We've now seen how we can solve reactor mole balances if we know the reaction rate as a function of conversion. But in general, rate equations are given in terms of species concentrations, not conversion. So in this video, we'll develop the relationships between conversion and concentration. So this will require a little bookkeeping, tracking the amounts of all species as the reaction proceeds. So let's consider the general reaction A plus B going reversibly to C plus D, where the lowercase symbols are the stoichiometric coefficients of each species. So taking A as our basis of calculation, assuming it's the limiting reactant, we can rewrite this in a form that looks like this. So our goal again is to find relationships between the concentration of each species and the progress of the reaction, or the conversion. We'll first look at the case of batch systems, then look at how this works for flow reactors. Remember, if we're interested in the number of moles of a species in our reactor at any time t, we can describe this in terms of conversion. So let's remember how we did this. So we could write the number of moles of some species A in the reactor at time t as the number of moles which we charged into our batch reactor at time equals 0 minus the number of moles reacted. Now we could further break down the number of moles reacted into the number of moles of A fed at time equals 0 times the number of moles reacted per mole of A fed. Now that last term is just the definition of conversion. So we can write this as the number of moles of A fed at time equals 0 times the conversion, which tells us per mole of A that we put into the reactor, how many react. So for any other species other than A, we can write the number of moles at any time just based on the reaction stoichiometry. So the number of moles at any time is just going to be how many we initially feed minus how many react. So if we want to describe, for example, for B, how many moles react, we can do this quite simply using the conversion of A and the reaction stoichiometry. So if we can rewrite the number of moles of B reacted as the moles of B reacted divided by the moles of A reacted times the moles of A reacted. Now why this is convenient is because this first ratio we can write simply from the reaction stoichiometry. So for every mole of A that reacts, B over A, where B over A are the stoichiometric coefficients of B are reacted. And this second term, the number of moles of A reacted, we just wrote as the initial number of moles of A fed times the conversion. So it's useful to set up a stoichiometric table for keeping track of things. So here I'll write for a different species the initial number of moles, the change in moles, so how many react as a function of conversion. So this is going to be a function of our conversion x, and then we will have our number of moles of that species remaining. So this will be our number of moles of that species at any time t. So here we want to describe our reactants A and B and products C and D. We can also, for generality, have some inert species, and then we'll keep track of the total number of moles in our system. Okay, so if we, for an arbitrary case, start with some initial number of moles in our batch reactor of each species, and we'll just label this N, A, B, C, and D naught, and we'll add some inert as well. then the total number of moles, which we'll write NT naught, is equal just to the summation of the initial number of moles for all of our species. So the change, the number of moles reacted, we can write from the stoichiometry. So for A, the change will be minus Na naught times the conversion X. So the sign here is negative because A is a reactant, so the number of moles is decreasing with time. For B, similarly, it's a reactant, but the stoichiometry is different, so we have to take the ratio of the stoichiometric coefficients of A and B to give us the change in number of moles of B. You can write a similar expression for our two products, and again, we have this initial term, that's the ratio of the stoichiometric coefficients, because initially we divided our entire reaction stoichiometry by the stoichiometric coefficient of A to put everything on a per mole A basis. That's useful because now we can express everything in terms of the conversion of A. So for our inert species, it doesn't undergo any reaction, so the amount remaining will be the same as we had initially. So the amount remaining is just going to be, for every species, how much we fed and how much was consumed or produced during the reaction. So for our products, the number of moles will be decreasing. And for our products, we'll have an increase in the number of moles with time. And for our inert, we will just have the same number of moles coming out as what we started with. So our total number of moles is going to be dependent on how many we started with at the beginning of the reaction, and also the reaction stoichiometry and progress. So if we have a higher number of moles of products than reactants in our stoichiometry, there's going to be an increase in number of moles as the reaction proceeds. Conversely, the total number of moles will decrease as the reaction proceeds if there are more total stoichiometric coefficients of the reactants are larger than those of the products. Okay, so we've now written everything in terms of total number of moles, but if we want to instead know concentrations as a function of conversion, we can simply write that the concentration of some species, say A, is equal to the number of moles of A divided by the reactor volume. So we wrote Na. Now from our stoichiometric table, we have an expression for that in terms of conversion. Similarly, we can write this for all of our other species. So this is just equal to the number of moles of B divided by the reactor volume. And the number of moles of B we expressed as the initial number of moles of B minus the amount reacted, which was the ratio of the stoichiometric coefficients of A and B, times the number of moles of A reacted, Na naught times X. And we'll have similar expressions for our products as well. Now we just need to consider if the volume is a function of conversion to obtain our desired rate as a function of conversion. In most situations for our batch stirred tank reactor, it's reasonable to assume constant volume, that is, V equals V naught. This could be because we have a gas phase reaction where the volume is fixed by the reactor volume, or a liquid phase reaction where the reaction takes place in a solvent so that the density is unaffected as reactants are converted into products. In these cases, the situation becomes quite simple. So if we can write in all of these situations that our reactor volume is a constant V0, then we can re-express. So if V equals V0, then Ca we could rewrite as Na0 times 1 minus x over V0. And so this term, which I'll highlight here, is simply the initial concentration Ca0. So you can rewrite this as Ca0 times 1 minus x. Similarly for Cb, you can write Mb0 minus B over A times Na0 times the conversion divided by V0. And so this will be Cb0 minus B over A times Ca0 times the conversion. So we can express this a little bit differently. So this could be rewritten as Ca0 times the ratio of the initial concentrations of B and A minus the ratio of the stoichiometric coefficients times the conversion. Okay, so we'll write for completion the similar expressions for Cc and Cd. Okay, so now we have a series of equations that we can use to convert from concentration, which we might see in a rate expression, to conversion, to then solve our reactor mole balances in terms of conversion if that's convenient. So this was all for our batch systems, and so in the next part of the video we'll look at the same situation for our flow systems. For flow systems, a very analogous treatment is possible. We can develop again a stoichiometric table where now we're keeping track of molar flow rates of species rather than the total number of moles. In this case, the concentrations are going to be given by, let me write for some species A, the molar flow rate of A divided by the volumetric flow rate. So in terms of units here, molar flow rates are units of moles per time. Volumetric flow rates are units of volume per time. So this gives you the expected units of concentration of moles per volume. Okay, so again, going back to our general reaction, where we've divided everything through by the stoichiometric coefficient of A to put it on a per mole of A basis, we can write the concentration of every species as its molar flow rate divided by the volumetric flow rate. And so the expressions here will be identical to what they were for the batch system, with molar flow rates taking the place of total number of moles, and the volumetric flow rate through the reactor taking the place of the reactor volume. So here for A, this is simply going to be the inlet molar flow rate times 1 minus the conversion divided by the volumetric flow rate. For Cb, we'll have a similar expression as we did for the batch system. So our expression depends on the inlet molar flow rate of A, the ratio of the stoichiometric coefficients of B and A, and then the amount of A reacted. So that's FA0, our inlet molar flow rate, times the conversion X. And the denominator here again is the volumetric flow rate through the reactor. So for the concentration of C, again, that's just going to be the molar flow rate of C divided by the volumetric flow rate. So that depends on how much C we fed initially, and then that molar flow rate of C is going to increase as the reaction proceeds, and the amount of C that we are producing depends on the ratio of the stoichiometric coefficients of C and A, and how much A is being reacted. And then we'll have an identical expression for D. Okay. So for the case of constant density, that is that the volumetric flow rate is equal to the initial volumetric flow rate at any position in the reactor, the case is going to become quite simple to describe, so that the inlet molar flow rate of any species, let's say A, divided by the inlet volumetric flow rate is just going to be the inlet concentration. So this could be the case if we have a liquid phase reaction, say happening in a CSTR, for example, or a gas phase reaction where there's no change in the number of moles, or if the gas phase reactants and products are highly diluted in an inert, such that the flow properties are not really dictated by the progress of the reaction. So for that situation, if we wanted to write this for A, for example, this would again be just FA naught times 1 minus x divided by now the constant volumetric flow rate through the reactor. And so this is just going to be the initial concentration times 1 minus x. I'll just show this for one more species, for CB. So this would be FB naught divided by the inlet volumetric flow rate minus B over A times FA naught divided by the inlet volumetric flow rate times the conversion. So this looks a lot like our situation for the batch reactor, where we have CA naught times the ratio of initial concentrations minus B over A times the conversion. But we will encounter situations that the volumetric flow rate is not constant. So for instance, in a gas phase reaction with a change in number of moles, so say for example for the ammonia synthesis reaction, which is N2 plus 3H2 going to 2 molecules of ammonia, you can see that we're coming in with 4 molecules of gas phase reactants, and as the reaction proceeds it just goes to 2, and so the volumetric flow rate is going to decrease as the reaction proceeds. So to describe these changes for a gas phase reaction, we can write the total concentration of gas phase species at any arbitrary point in the reactor. So we can write the total concentration as the total molar flow rate of all species divided by the volumetric flow rate. And so this is equal to the pressure in the reactor for a gas phase reaction divided by the gas constant times the temperature. So dividing this expression by the total inlet concentration gives us an expression we can solve for the volumetric flow rate. So let's just write that CT naught equals the total inlet molar flow rate divided by the inlet volumetric flow rate, and that's equal to the initial pressure in the reactor divided by gas constant times the initial temperature. So again, here I'm going to divide these two expressions by one another and solve for the volumetric flow rate. So this comes out to the volumetric flow rate at any position in the reactor is equal to the inlet volumetric flow rate times the ratio of the total molar flow rate at any position divided by at the inlet times the ratio of the initial pressure to the pressure at our position downstream times the ratio of the temperature to the initial temperature. Similarly, if I wanted to write the concentration of any species J, I could write that as the initial total concentration times the ratio at any point of the molar flow rate of J to the total molar flow rate times this ratio of our pressure at the position of interest divided by the initial pressure and the initial temperature relative to the temperature where we are. So again here the molar flow rate of J and the total molar flow rate are going to be functions of x, which we can track using our stoichiometric table. So now we've arrived at expressions that we can use to relate concentrations to conversions such that we can insert conversion into our rate equation and solve reactor design problems. So we'll see an example of this in the next video.